Imagine a wall calendar. Monday, Tuesday, Wednesday, all the way to Sunday. Then what comes next? Monday again. The whole week repeats, over and over, every 7 days. That is exactly what a periodic means, something that repeats its values at regular, predictable intervals. The length of that repeating block is called the period. For the days of the week, the period is 7 days. One complete run through the pattern, from Monday to Sunday, is called a cycle. A periodic function is just a mathematical version of this idea, a graph that copies the same shape again and again, forever, with a fixed gap between copies. Why do we care if something repeats? Because if you understand one complete cycle, you understand the whole thing, forever. You can predict what happens next without doing any new work. Think of a heartbeat on a monitor. It goes blip, pause, in a steady rhythm. Doctors only need to see one healthy beat to know the pattern. In the same way, many things in nature are periodic: the swing of a pendulum, the phases of the moon, the rise and fall of tides, even the vibration of a guitar string. In your JEE preparation, periodic functions let you study a graph over just one period and instantly know its behavior everywhere else. They are the building blocks of waves, sound, alternating current, and planetary orbits. Let us see this on a graph. Picture a wavy shape that goes up and down. Pick a point on the x-axis. Now slide the whole graph to the right by a certain distance. If the shifted graph lands perfectly on top of the original, then the function is periodic. That shift distance is the period, which we usually call capital T. Mathematically, we write this as f of x plus t equals f of x. It means the value of the function at any point is the same as its value one period later. The period t is the smallest positive number that makes this true. If a pattern repeats every 10 units, it also repeats every 20 or 30, but we always name the smallest one as the period. On the animation, you can see a highlighted segment that repeats exactly. The length of that segment, marked on the x-axis, is the period. Let us solve a concrete problem. Imagine a giant Ferris wheel that takes exactly 30 minutes to complete one full rotation. Your height above the ground goes up and down as the wheel turns. After 30 minutes, you are back at the very bottom, and the whole pattern of your height starts again. This means your height as a function of time is periodic, with a period of 30 minutes. Now, here is the power of the idea. What is your height 10 minutes after the start? Suppose you measure it and find it is 12 meters. Then, without any extra measurement, you know that your height at 40 minutes is also 12 meters. Why? Because 40 minutes is exactly one period after 10 minutes. The shape repeats. The same logic works for any time, just add or subtract 30 minutes to find matching heights. So the whole idea is, a periodic function gives you the future for free, once you know one full cycle. Imagine a clock hand that starts pointing straight to the right, at 3 o'clock. An angle is simply how much that hand has turned. Now, instead of a clock, picture a circle with a radius of exactly 1 unit, centered at the origin of a graph. We call this the unit circle. If we put a dot on the circle and let it travel around, its position at any moment is given by two numbers, how far up or down it is, and how far left or right it is. The up-down coordinate is what we call the sine of the angle. The left-right coordinate is the cosine. So sine and cosine are just the y and x of a point moving on a circle. Why do we care about a dot on a circle? Because so many things in the world go round and round, or wiggle back and forth. Think of a Ferris wheel. As the wheel turns, your seat goes up, then down, then up again, repeating forever. If you plot your height above the ground against time, you get a wave. That wave is exactly the sine function. Sound waves, light waves, even the alternating current in your wall socket, they all follow this same smooth, repeating pattern. Since the dot on the circle takes exactly one full turn, which is 2 pi radians, to get back to its start, both sine and cosine naturally repeat every 2 pi. They are the simplest periodic functions, the building blocks of all waves. Let's build this step by step. We begin with our dot at the rightmost point of the circle, coordinates 1, 0. This is angle 0. Now we rotate the radius counterclockwise by some amount. How do we measure that rotation? Not in degrees, but in radians. 1 radian is the angle you get when you wrap the radius along the circle's edge. Since the full circle's edge is 2 pi times the radius, a full turn is exactly 2 pi radians. As the dot moves, its x-coordinate, which we call cosine theta, shrinks from 1 down to 0 at the top, then to -1 at the left, and back. The y-coordinate, sine theta, rises from 0 to 1 at the top, falls to 0, then to -1 at the bottom. After a full 2 pi radian turn, the dot is right back at 1, 0, so cosine of 2 pi is 1, and sine of 2 pi is 0. The cycle is complete and ready to repeat. Let's solve a real problem. A Ferris wheel has a radius of 10 meters, and its center is 12 meters above the ground. You get on at the bottom. As the wheel turns, your height changes. The angle theta is measured from the 3 o'clock position, but our seat starts at the bottom, which is a quarter turn behind, or -pi/2 radians. To keep it simple, let's just find your height when you are at the very top. At the top, the angle is pi/2 radians, straight up. The sine of pi/2 is 1. Your height above the center is the radius, 10 meters, times the sine, which is 10 meters. Add the center's height of 12 meters, and you are 22 meters up. The formula for your height at any angle is 12 plus 10 times sine of theta. This is the power of sine, it turns circular motion into an up-down number we can use. You already know that the sine function, sin of x, is a wave that repeats itself exactly every 2 pi radians. That distance along the x-axis for one full cycle is called its period. Now, what if we put a multiplier b inside, like sin of bx? The wave still has the same shape, but it gets squeezed or stretched horizontally. A bigger b packs more cycles into the same space, so the period shrinks. The new period is 2 pi divided by b. For example, if b is 2, the wave completes a full up and down twice as fast, so its period is just pi. Why would we want to change the period? Imagine you're describing something that repeats in time or space, like a musical note vibrating hundreds of times a second, or the temperature going up and down once a year. The basic sine wave has a period of 2 pi, which is just a number on paper. To make it match a real-world rhythm, you need to stretch or squeeze it so one cycle equals the actual length you care about, like 1 second or 1 day. The B factor is the knob that lets you dial in exactly how fast the wave oscillates. It turns the abstract sine curve into a tool for modeling any regular back and forth pattern. Let's derive where the formula period equals 2 pi over b comes from. Think about what makes sine repeat. The sine function completes one full cycle when its input angle increases by 2 pi radians. That's just what a period means for sine. Now, if the input is b times x, we want to know how much x must change to make that input grow by 2 pi. We set up the equation, b times the change in x equals 2 pi. Solving for the change in x gives 2 pi divided by b. That's the new period. This idea works for any periodic function, not just sine. If a function f of x has period p, then f of k times x has period p divided by the absolute value of k. The absolute value just ensures the period is always positive, since a negative k just flips the graph left to right without changing the cycle length. Let's use this to solve a concrete problem. A tuning fork vibrates at 440 Hz, which means 440 cycles per second. We want to model the air pressure as a sine wave with time t in seconds. We need a b that makes the period exactly 1/440th of a second. Using our rule, period equals 2 pi over b, we set 1/440 equal to 2 pi over b. Solving for b gives b equals 2 pi times 440, which is 880 pi. So the pressure wave is sine of 880 pi times t. At t equals 1/440th of a second, the input is 880 pi times that, which simplifies to 2 pi, exactly one full cycle. The same method lets you dial in the period for any wave. Just set 2 pi over b equal to your desired cycle length and solve for b. You already know that sine and cosine are waves that repeat every 2 pi radians, that's their period. But real waves in the world are rarely that simple. A sound can be loud or soft, a tide can start early or late, and a swing might not be centered at ground level. Today we meet three knobs that let us shape a sine wave to match any real situation, without changing how fast it repeats. Amplitude controls how tall the wave is, the distance from its calm middle to a peak. Phase shift slides the whole wave left or right along the horizontal axis. And vertical shift moves the wave's midline up or down. Think of a basic sine wave as a lump of clay. These three tools let you stretch it taller, nudge it sideways, and lift it higher, all while keeping its repeating rhythm exactly the same. Imagine you're an engineer designing a Ferris wheel. A basic sine wave tells you your height goes up and down, but it always starts at 0 and swings between -1 and +1. A real Ferris wheel is 30 meters tall, starts at the bottom when you board, and its center is 15 meters above the ground. Without amplitude, phase, and vertical shift, sine is stuck in a tiny box. It can't describe the actual world. Amplitude lets you set the wheel's radius, phase shift sets your starting angle, and vertical shift lifts the whole ride to the right height. These three ideas turn a bare mathematical wiggle into a precise model of anything that oscillates: sound volume, alternating current voltage, hours of daylight through the year, even your heartbeat on a monitor. They are the difference between a textbook curve and a tool that solves real problems. Let's build the full formula piece by piece, starting from the plain sine wave you already know. First, amplitude. If we multiply the whole function by a number a, we stretch every height by that factor. The peaks, which were at 1, now reach a, and the troughs reach -a. The wave's middle stays at 0, but its height from middle to peak becomes a. That's why amplitude is half the total height from bottom to top. Next, phase shift. Inside the sine, we replace x with x minus c. This is a horizontal slide. When x equals c, the inside becomes 0, so the wave's starter moves to x equals c. If c is positive, the whole wave shifts right by c. Finally, vertical shift. We add a number d to the whole function. This lifts every point up by d, so the midline moves from 0 to d. The wave now oscillates between d minus a and d plus a. Let's use these knobs to model a real tide. Suppose high tide reaches 5 meters and low tide falls to 1 meter, with a full cycle every 12 hours. We want a sine function that fits this. First, amplitude. The total height change is 5 minus 1, which is 4 meters. Amplitude is half of that, so a equals 2 meters. Next, vertical shift. The midline sits exactly halfway between high and low, so we average them. 5 plus 1 over 2 gives 3 meters. That's our d. Now phase shift. A plane sine wave starts at 0 and rises. but our tide at time 0 might be at high tide, which is a peak. A sine wave peaks when its inside is pi over 2 radians. So we need x minus c to equal pi over 2 when x is 0. That means c is negative pi over 2, which is a shift left by pi over 2. We already know sine and cosine from the unit circle. Now meet their close relatives. Tangent is simply sine divided by cosine. On the circle, think of a line from the origin to a point on the edge. The slope of that line is the tangent. So tangent tells us how steep that radius is. We also have 3 flip-side functions called reciprocals. Secant is 1 over cosine. Cosecant is 1 over sine. And cotangent is cosine over sine, which is 1 over tangent. They all come from the same circle family, just looking at different ratios. Why do we need these extra functions? Sine and cosine give us coordinates on the circle. But real life often asks a different question: how steep is something? Imagine a ladder leaning against a wall. The height the ladder reaches is sine, the distance from the wall is cosine. But the steepness of the ladder is the height divided by the distance, which is tangent. So tangent answers the how steep question directly. The other functions, secant, cosecant, and cotangent, just flip these ratios upside down. They pop up naturally in equations and later in calculus, so it is good to know them as a complete set. Now the interesting part: tangent has its own rhythm. Sine and cosine take a full circle, 360 degrees or 2 pi radians, to repeat. But tangent repeats after just half a turn, 180 degrees or pi radians. Why? Look at the circle. A radius pointing at some angle has a certain slope. If you spin it exactly 180 degrees, it points the opposite way, but the line it makes is the exact same line, so the slope is identical. That means tangent's period is pi. Also, when cosine is 0, at 90 and 270 degrees, the radius is straight up or down. The slope is infinite, so the tangent graph shoots off to infinity there. We call those vertical asymptotes. Secant and cosecant have period 2 pi like cosine and sine, but they also have breaks where their denominator is 0. Let us use tangent to solve a real problem. You stand 10 meters from a tree and measure the angle from the ground to the top as 60 degrees. How tall is the tree? Tangent of the angle is the tree's height divided by your distance. So height equals distance times tangent of 60 degrees. Tangent of 60 degrees is root 3, which is about 1.732. Multiply by 10 meters, and the tree is about 17.32 meters tall. Notice we did not need the leaning ladder's length, just the ground distance and the angle. Tangent gave us the height directly. The same method works for any tall object, a building, a mountain, even a star if you know the baseline. You already know that a periodic function repeats its shape every period t. Now we look at its derivative, the slope at every point. Imagine tracing a sine wave with your finger. At the peak, the slope is flat, 0. On the way up, the slope is positive and steep. On the way down, it's negative. Because the wave repeats, this whole pattern of slopes also repeats exactly after one period. So the derivative of a periodic function is also periodic, with the same period t. It's like the shadow of the repeating shape, the steepness rhythm just cycles along with the original. Why do we care that the derivative repeats? Because in physics and engineering, many systems are driven by periodic forces, like a swing pushed at regular intervals, or alternating current in a wire. Knowing the derivative pattern lets us predict velocity, acceleration, or current change at any point in the cycle. Even more powerful is the integral property. the area under one full period of a periodic function is always the same number, no matter where you start measuring. This is the foundation of Fourier analysis, where we break any periodic signal into simple sine waves. It means the average value over a cycle is fixed, which is crucial for designing circuits, analyzing sound, and solving differential equations. Let's derive this from the unit circle you already know. Picture a radius spinning. The height of the point is sine of the angle, and the horizontal shadow is cosine. As the angle increases at a steady rate, the height wiggles up and down, that's the sine wave. Now, how fast is the height changing? When the point is at angle 0, height is 0 but moving up fastest, that's cosine of 0, which is 1. So the derivative of sine is cosine. Similarly, the horizontal shadow's rate of change is negative sine. This gives a beautiful cycle. Differentiate sine, you get cosine. Differentiate cosine, you get negative sine, again gives negative cosine, and one more brings you back to sine. For the integral, imagine shifting the starting point by a quarter period. The area under one full hump of sine from 0 to 2 pi is exactly the same as from pi over 2 to pi over 2 plus 2 pi. Let's solve a concrete problem. Household AC voltage in India is a sine wave, V of t equals 170 times sine of 120 pi t. The period t is 1 over 60 seconds, because the frequency is 60 Hz. We want the average voltage over a full period. Using the integral property, we compute the area under one cycle from 0 to t. The integral of sine over a full period is 0 because the positive hump cancels the negative hump exactly. So the average voltage is 0. But that doesn't mean no power is delivered. The effective value is the root mean square, or RMS, which is the peak divided by root 2, about 120 volts. This RMS value is what your multimeter shows. The key insight, the integral over a period being constant, lets us calculate average power, filter signals, and design everything from radios to power grids. Imagine a single, pure musical note, like the one a tuning fork makes. If you could see the air pressure near your ear, it wouldn't be still. It would be going up and down, squeezing together and spreading apart, in a perfectly smooth, repeating pattern. That pattern is exactly a sine wave. The horizontal axis is time, and the vertical axis is the air pressure. The number of complete up and down cycles the wave makes every second is called its frequency. A higher frequency means a higher pitch note. The time it takes to complete just one cycle is called the period. Frequency and period are like two sides of the same coin. If a wave has a frequency of 440 cycles per second, its period is 1/440th of a second. Why do we care so much about sine waves? Because they are nature's favorite way to repeat things. The back and forth of a guitar string, the yearly cycle of temperature, the alternating current in your wall socket, even your body's sleep-wake rhythm, they all trace out sine waves. But the real world isn't just pure tones. A violin playing the same note as a flute sounds different because its wave is a richer shape. That shape is built by adding together many pure sine waves of different frequencies, like stacking ripples in a pond. And this is where calculus becomes our superpower. With derivatives, we can ask, how fast is the temperature rising right now? With integrals, we can ask, what is the total energy carried by this sound wave over a second? Calculus is the tool that lets us measure and understand these changing rhythms. Let's build this from the ground up. You already know the basic sine function, sin of t. On its own, it completes one cycle every 2 pi seconds. To make it match a real sound, we need to set its frequency. We do that by multiplying t by 2 pi times the frequency, f. So a pure tone with frequency f is sin of 2 pi ft. Now, to make a complex sound, we just add waves. Imagine we take our first wave, sin of t, and add a second, faster wave, sin of 2t. At each moment in time, we simply add their pressures together. The new wave is no longer a perfect, simple sine. It has bumps and wiggles, a new shape is born. This is the core idea. Any repeating shape can be built by adding a fundamental sine wave to its harmonics, which are sine waves at integer multiples of the fundamental frequency. Let's solve a real problem. We want to model the average daily temperature in a city over a year. We know it's hottest in midsummer and coldest in midwinter, so it roughly follows a sine wave. Let's say the average temperature over the whole year is 15 degrees Celsius, and it swings up and down by 20 degrees. We'll set T equals 0 at the start of the year. A good model is temperature T of T equals 15 plus 20 times the sine of 2 pi T over 365. The 365 is our period in days, so the wave completes one cycle in a year. Now, a calculus question: on which day is the temperature rising the fastest? The rate of change is the derivative, dt. The derivative of a constant is 0, and the derivative of the sine is a cosine, multiplied by the chain rule. We get dt equals 20 times cosine of 2 pi t over 365, times 2 pi over 365. We've been on a journey about periodic functions, functions that repeat their pattern over and over. The length of one full repeat is called the period. At the heart of it all are sine and cosine, born from a point spinning on the unit circle. They complete one full cycle every 2 pi radians. But real-world cycles aren't always that simple, so we learn to stretch, squeeze, slide, and lift these basic waves using amplitude, period changes, phase shifts, and vertical shifts. That lets us mold them to fit things like sound waves, tides, or the seasons. Why did we spend so much time on this? Because the world is full of cycles. Your heartbeat, the vibration of a guitar string, the rise and fall of the sun each day, they're all periodic. Sine and cosine give us a single, clean language to describe any of them. Even better, calculus plays nicely with these rhythms. The derivative of a periodic function is still periodic, and the area under one full cycle is a fixed number you can rely on. So once you understand sine and cosine, you have a key that unlocks a huge range of problems in physics, engineering, and beyond. Let's rebuild the big picture from scratch. Imagine a wheel with a radius of 1 unit. As it spins, the height of the tip above the center traces out a sine wave. The horizontal shadow traces cosine. That's the core engine. To make it match a real signal, we change the amplitude, how tall the wave is, by multiplying. We change the period, how fast it cycles, by multiplying the angle inside. We slide it left or right with a phase shift, and lift the whole thing up or down with a vertical shift. Other trig functions like tangent and secant are just ratios of these same shadows, and they have their own repeating patterns and special breakpoints called asymptotes. Let's put it all together with a concrete example. Imagine a child on a swing. The swing's position in meters, forward and back, over time t in seconds, is given by y equals 2 times the sine of pi times t. The amplitude is 2 meters, that's how far they swing from the center. The period is 2 seconds, because after 2 seconds the sine function has completed one full cycle. If we take the derivative to find velocity, we get v equals 2 pi times cosine of pi t, still a periodic function, just shifted. And if we integrate over one full period, from 0 to 2 seconds, the net area is 0, because the forward and backward motion cancel out. That's the whole idea. A simple spinning circle gives us a language to describe, predict, and analyze any repeating rhythm in the universe.